The construction of an aircraft carrier begins with extensive planning and design. This initial phase involves naval architects, engineers, and defense experts. These specialists collaborate to define every system and structural element of the vessel. Detailed planning ensures the carrier meets complex, operational, and strategic requirements. Modern aircraft carriers, such as the Ford class, represent peak engineering complexity. Their construction relies on thousands of highly detailed digital blueprints. These blueprints provide precise specifications for every component and assembly. This meticulous planning ensures the carrier's structural integrity and operational efficiency. Before physical construction, advanced computer simulations are crucial for carrier design. These simulations rigorously test the carrier's stability under various conditions. Survivability is also assessed, ensuring the vessel can withstand potential threats. Aircraft launch and recovery operations are meticulously simulated for efficiency and safety. This virtual testing phase identifies and resolves design flaws early. Ultimately, simulations ensure optimal performance and enhance safety for the final carrier. The commencement of physical construction is a critical milestone in any project lifecycle. This phase is strictly contingent upon the formal approval of all preceding design plans. Design approval signifies that all architectural and engineering specifications have been met. It confirms compliance with all relevant building codes, safety standards, and regulations. Operational requirements, including functionality and usability, are also thoroughly vetted. Only after this comprehensive review and approval can construction physically begin. Aircraft carriers are not built as single, monolithic structures. Their construction utilizes a modular approach, breaking down the process into manageable sections. These large prefabricated components are known as supermodules. This method significantly enhances both the efficiency and precision of the construction process. Supermodules are substantial components in large-scale construction projects. Each individual section of a supermodule possesses immense weight. These sections typically weigh between 500 and 1,000 tons. This weight reflects the immense scale and structural integrity required for the vessel. Within vast construction halls, steel plates are prepared for processing. Advanced plasma systems are utilized for precise cutting operations. Laser technology further enhances the accuracy of steel plate fabrication. These precisely cut foundational pieces form the core of each module. Robotic welding systems are employed for precision fabrication in industrial settings. These systems utilize automated arms to perform intricate welding tasks. The process involves meticulously fusing thick, naval-grade steel components. This specialized steel requires precise handling due to its robust properties. Robotic welders ensure strong and durable connections within module structures. This automation guarantees consistent quality and structural integrity in critical applications. Essential internal systems are integrated early within each module during the construction process. These systems include critical components such as pipes, electrical wiring, and ventilation ducts. Structural supports are also installed at this stage, ensuring the module's integrity. This early integration significantly streamlines the overall assembly and construction process. Modular construction is an innovative building method that involves fabricating sections off-site. These pre-engineered modules are then transported to the construction site for assembly. This approach significantly reduces the overall construction timeline compared to traditional methods. Manufacturing in a controlled factory environment enhances the precision of each assembled section. The controlled conditions minimize errors and improve quality control for all components. This method leads to faster project completion and higher structural integrity. Once construction of the massive modules is completed, they are prepared for transport. Giant cranes, specifically designed for heavy lifting, are deployed to handle these structures. These cranes carefully lift each module, demonstrating precise control and engineering. The modules are then transported to a designated dry dock area. Within the dry dock, each module is meticulously maneuvered into its exact position. This alignment process requires extreme precision to ensure structural integrity and functional fit. The construction process involves the meticulous alignment of individual modules in a dry dock. These modules are then precisely welded together, forming the foundational sections of the vessel. This critical welding phase ensures structural integrity and watertight seals for the carrier. Gradually, through this sequential assembly, the complete structure of the carrier takes shape. The hull serves as the fundamental structural foundation of an aircraft carrier. It forms the backbone of the vessel, providing its primary shape and integrity. The hull is engineered to endure the most extreme maritime conditions encountered at sea. It is also designed to withstand significant operational stresses during deployment. This robust construction ensures the carrier's stability and survivability in diverse environments. The hull's robust design is engineered to withstand extreme conditions. It is built to survive violent storms and heavy aircraft landings. The hull also endures high-speed movement and potential combat damage. These tests demonstrate the hull's structural integrity and resilience. High-strength naval steel is a specialized material crucial for maritime vessel construction. It is exclusively utilized throughout the hull, forming the primary structural integrity of the ship. This type of steel is engineered to provide superior durability against harsh marine environments. Its composition ensures exceptional resilience, vital for resisting impact and fatigue. The exclusive use of naval steel guarantees the vessel's longevity and operational safety. Watertight bulkheads are critical structural components within a vessel's hull. These bulkheads divide the internal compartments of the hull into sealed sections. Their primary function is to prevent the spread of water in case of hull damage. If one section is compromised, the bulkheads ensure other areas remain sealed. This design feature protects the integrity of the vessel and its contents. It is a vital safety measure, enhancing buoyancy and survivability in maritime operations. The watertight bulkhead system is a critical survivability feature in marine vessels, particularly carriers. Its primary function is to contain damage within specific compartments of the vessel. This containment is crucial for preventing the widespread flooding of the ship. By isolating damaged sections, the system maintains the vessel's buoyancy and stability. Ultimately, it significantly enhances the carrier's ability to survive incidents at sea. The construction of large vessels necessitates an immense quantity of raw materials. A significant portion of this material is dedicated to the lower hull structure. The lower hull alone can weigh tens of thousands of tons. This weight highlights the substantial material requirements for such massive vessels. The scale of these components underscores the engineering challenges involved in shipbuilding. These material demands reflect the need for structural integrity and durability in marine environments. An aircraft carrier is undergoing construction within a dry dock facility. The massive structure of the carrier already towers impressively above the dock floor. Its immense scale is evident, resembling a horizontal steel skyscraper. This stage of construction highlights the significant engineering involved in shipbuilding. The dry dock provides a controlled environment for assembling such a large vessel. The visible steel framework indicates the advanced progress of the carrier's hull and superstructure. Modern U.S. aircraft carriers utilize advanced nuclear propulsion systems for power generation. These systems employ nuclear reactors as their primary energy source. This design choice represents a significant departure from traditional diesel engines. Nuclear reactors provide the necessary energy to propel the massive vessels. They also power all onboard systems, enabling extended operational periods. This technology ensures sustained speed and endurance without frequent refueling. Nuclear reactors are central to generating electricity through controlled nuclear reactions. The process begins with precisely managing these reactions to produce significant amounts of heat. This controlled heat generation is the fundamental initial step in the power production cycle. The thermal energy released is then used to heat a working fluid, typically water. Ultimately, this heat drives turbines to generate electricity, completing the power generation process. Heat energy is a fundamental input for various industrial and propulsion systems. This heat is precisely applied to water within a controlled environment. The application of heat causes the water to undergo a phase transition, converting it into steam. This generated high-pressure steam is a critical component in the overall propulsion cycle. High-pressure steam is directed towards massive turbines within the power generation system. This steam's energy causes the turbine blades to rotate rapidly, initiating a mechanical process. The rotation of the turbine signifies the conversion of thermal energy from the steam. This thermal energy is efficiently transformed into mechanical energy, driving subsequent power generation. The propulsion system of a ship relies on a series of interconnected mechanical components. Central to this system are turbines, which generate rotational power. These turbines are engineered to drive robust propeller shafts. The propeller shafts transmit the rotational force to the ship's propellers. This action ultimately propels the massive vessel through water. ensuring its movement. Nuclear propulsion systems offer exceptional operational endurance for ships. This advanced nuclear system powers the vessel for extended periods. It enables the ship to operate for over 20 years without requiring refueling. This capability provides unparalleled operational autonomy and range. Such long refueling cycles significantly reduce maintenance and logistical demands. The system is engineered to generate a substantial amount of electrical power. This power output is sufficient to meet the energy demands of a small city. It effectively supports all onboard operational requirements and systems. This ensures robust and continuous energy supply for complex operations. The installation of a nuclear propulsion system is a critical phase in carrier construction. This process is recognized as one of the most complex engineering tasks. It demands the highest levels of security due to the nature of the technology. The successful integration of the system is vital for the carrier's operational capabilities. The installation of a nuclear system demands the highest level of safety and precision. Strict safety protocols are paramount to prevent incidents and ensure operational integrity. Every step of the installation process is meticulously planned and executed. Precision engineering ensures that all components fit and function flawlessly. Adherence to these stringent measures is critical for long-term safety and reliability. These protocols safeguard personnel, the environment, and future operations. The flight deck is a critical and defining feature of an aircraft carrier. It is uniquely engineered to facilitate continuous flight operations at sea. This specialized platform supports the launch and recovery of various aircraft. Its design integrates complex systems for efficient and safe aviation maneuvers. The flight deck enables an aircraft carrier to project air power globally. Aircraft carrier decks are engineered to endure extreme forces during flight operations. They must withstand the impact of 3 zero-ton fighter jets landing at high speeds. The deck material also resists the intense heat generated by powerful jet blasts during takeoffs. This structural integrity is crucial for continuous and safe aircraft operations at sea. The flight deck is engineered with a robust, multi-layered construction. It incorporates layers of reinforced steel for structural integrity and durability. Specialized coatings are applied to withstand extreme temperatures encountered during operations. This design ensures resistance to significant physical stresses from aircraft landings and takeoffs. Aircraft carriers utilize sophisticated launch systems located beneath the flight deck. Older carrier models traditionally employ steam catapults to propel aircraft for takeoff. Newer generation carriers are equipped with electromagnetic aircraft launch systems, EMALS. These advanced systems provide efficient and powerful aircraft launching capabilities. Aircraft launch systems are engineered to accelerate aircraft from a complete standstill. These systems rapidly propel aircraft to takeoff speed in a matter of seconds. This rapid acceleration capability is crucial for efficient and timely deployment. Such technology enables quick and effective aircraft operations, enhancing strategic readiness. Arresting cables are critical safety components on aircraft carrier flight decks. These cables are strategically installed across the landing area. Their primary function is to facilitate the safe recovery of aircraft. Aircraft hook onto these cables, rapidly decelerating upon landing. This system ensures controlled and efficient stopping, even at high speeds. Aircraft carrier landings are critical maneuvers, requiring precise control and specialized equipment. The deck features multiple arresting cables stretched across the landing area. As a jet approaches for landing, a tailhook is deployed from its rear. This tailhook is designed to catch one of the arresting cables on the deck. Upon engagement, the cable rapidly decelerates the aircraft. This system brings the heavy aircraft to a complete stop in less than 100 meters. Aircraft launch and recovery operations involve immense forces and complex systems. These operations demand perfect calibration of all related systems. Precise calibration is critical to ensure both safety and operational efficiency. Any misalignment or error can have severe consequences for personnel and equipment. The island is a prominent superstructure on an aircraft carrier's flight deck. It serves as the command tower, rising above the main deck. This structure houses critical operational and control functions for the carrier. It is essential for flight operations, navigation, and overall ship management. The island's strategic placement ensures optimal visibility and control for the crew. Advanced navigation systems are integral for guiding large vessels. These systems provide critical data for safe and efficient maritime travel. They enable precise positioning and route planning across vast oceans. Such technology is crucial for the operational success of massive ships. Massive radar arrays are strategically integrated into the island island's infrastructure. These advanced systems are designed for long-range detection capabilities. They can effectively identify aircraft at distances of hundreds of kilometers. The arrays also possess the ability to detect ships over similar vast ranges. The island structure on an aircraft carrier houses critical air traffic control facilities. These facilities are essential for managing all aircraft movements on the carrier's deck. They also oversee aircraft operations in the airspace surrounding the carrier. Air traffic controllers ensure the safe and efficient flow of all flight operations. This centralized control is vital for coordinating takeoffs, landings, and aerial maneuvers. Combat command centers are critical operational hubs within military installations. These centers are responsible for coordinating both defensive and offensive military operations. They act as the strategic brain, processing intelligence and issuing directives. Their function is vital for effective command and control during combat scenarios. Aircraft carriers are complex vessels requiring vast amounts of power for operation. This power is distributed through an intricate network of electrical wiring. Thousands of kilometers of wiring crisscross the ship's interior. This extensive network forms the backbone of the carrier's electrical system. It ensures power delivery to all critical ship systems and components. This intricate wiring is essential for the carrier's functionality and operational readiness. Electrical systems are fundamental for powering essential functions across various platforms and facilities. These systems supply energy for critical operational components, such as radar and communication equipment. They also support mechanical systems, including aircraft elevators and maintenance infrastructure. Furthermore, electrical power is vital for sustaining crew living quarters and their daily needs. Defensive weapon systems are crucial for safeguarding against various threats. These systems are strategically installed to protect critical assets and personnel. One key component is missile interceptors, designed to neutralize incoming projectiles. Missile interceptors use advanced tracking and guidance to destroy threats mid-flight. Close-range defensive guns provide immediate protection against proximate dangers. Together, these systems form a multi-layered defense, enhancing overall security. A central combat management network integrates all onboard systems. This integration ensures seamless communication and data exchange between diverse components. It facilitates coordinated operation across all functionalities, from sensors to weaponry. The network enables rapid and effective response to dynamic combat scenarios. System integration testing, SIT, is a critical phase in software development. Its primary purpose is to verify that all integrated system components function cohesively. This comprehensive testing ensures seamless interaction between various modules and subsystems. SIT often involves extensive testing protocols, simulating real-world operational scenarios. The duration of SIT can span several months, depending on system complexity and scale. Successful SIT confirms system stability, reliability, and adherence to functional requirements. Aircraft carriers are massive vessels designed to house a substantial number of personnel. They typically accommodate between 4,000 and 5,000 individuals, forming a floating city at sea. This large crew complement necessitates extensive living facilities on board the carrier. Dedicated working spaces are also integrated to support diverse operational roles and tasks. Modern ships are designed to be self-sufficient, akin to a floating city. They incorporate comprehensive facilities to support extended voyages and diverse crew needs. Essential living spaces include dedicated sleeping quarters for all personnel. Onboard kitchens are equipped to provide regular meals, ensuring sustenance for the crew. Medical facilities are present to address health concerns and provide emergency care. Additional amenities like gyms, offices, and storage areas enhance functionality and comfort. Desalination plants are crucial for providing fresh water in environments with limited natural sources. This technology converts saline water, such as seawater, into potable fresh water. The process ensures a continuous and reliable supply of water for various needs. Onboard desalination is vital for vessels during long deployments, sustaining the crew. It eliminates reliance on stored water, enhancing self-sufficiency and operational range. Before final commissioning, an aircraft carrier undergoes rigorous sea trials. These trials are crucial for testing the vessel's maximum speed and maneuverability. Reactor performance is meticulously evaluated to ensure operational safety and efficiency. Aircraft launch and recovery systems are thoroughly tested under various conditions. Emergency protocols are practiced to ensure the crew is prepared for any contingency at sea.